In this video, we're going to discuss the photoelectric effect. The photoelectric effect was a well-known phenomenon, but it wasn't until 1905 that Albert Einstein used quantum theory to fully explain what was going on in the experiment. We observe the photoelectric effect when we shine light onto a metal surface. What we observe is that electrons are ejected from that metal surface. As a reminder, we are thinking about light here as a wave particle or a photon whose energy can be calculated using this expression, where E is equal to Planck's constant times the frequency, or E is equal to Planck's constant times the speed of light divided by the wavelength. The interesting thing about this experiment is that the kinetic energy of the electron that gets ejected from the surface is proportional to the energy of the photon incident on the surface. Here's what I mean by that. If a blue photon or a high frequency, high energy photon is incident on the surface, the electron that will be ejected from the surface will have a very high kinetic energy. Here I'm using this arrow to represent a vector for the kinetic energy of the electron. If we shine a green photon, that photon has slightly lower energy and a slightly lower frequency, slightly longer wavelength than the blue photon. The kinetic energy of the electron that's ejected by the green photon is a little less. If we shine a red photon with even lower energy, lower frequency, longer wavelength, that photon does not have enough energy to eject the electron at all. If you perform this experiment and plotted the kinetic energy of the ejected electrons as a function of the frequency of the incident light, what you'd find is that there's a linear relationship between the kinetic energy of the electron ejected and the frequency of the incident light. The slope of this linear relationship is simply Planck's constant. The other thing that I'd like you to notice in this plot is that there is some threshold of frequency of incident light in order for any electrons to be ejected. In this particular graph, it's around 5 times 10 to the 14 hertz. That is, any frequency of light lower than 5 times 10 to the 14 hertz does not have sufficient energy to eject an electron. We call this the binding energy. So there's some amount of energy associated with the binding of the electron to the material that needs to be overcome by the photon before the electron can be ejected. The symbol for this is W. So now we have a complete expression for this line where the kinetic energy is equal to Planck's constant times the frequency minus the binding energy. Let's look at an energy diagram to try to understand this explanation a little bit better. The y-axis has been labeled as energy. The zero of energy differentiates between a free electron, that's an electron that's been ejected from the surface, and a bound electron, that's an electron that's still stuck in the material. The electron will reside at some energy level within the material. This is the bound electron. When the photon is incident on the surface, the energy of that photon will be transferred to one of these electrons. If that photon has enough energy to push the electron from the bound state into the free state, then that photon can eject the electron from the surface. The bound energy, or the binding energy, is represented here as W. So if a photon has at least that much energy, it will eject the electron. any additional energy that the photon has will turn into kinetic energy for the electron, for the free electron. Notice that here is the blue photon, where the arrow represents its total energy. It has enough energy to both eject the electron and give it some kinetic energy, to unbind it and give it kinetic energy. The green photon has enough energy to unbind the electron and give it some kinetic energy. But here, this arrow represents the total energy of the red photon. Notice that the red photon does not have enough energy to even eject the electron from the surface. So there are a few conclusions that we can draw from this experiment. First of all, I want you to note that for every one photon that is incident on the surface, one electron will be ejected. There's a one-to-one relationship between the subatomic particle, the photon, and the subatomic particle, the electron, that gets ejected. The second thing is that the electron kinetic energy is independent of light intensity. What that means is that if you are shining red photons on this surface, red photons do not eject electrons. It doesn't matter how bright the light bulb is that's shining that red light, those red photons have insufficient energy to overcome the binding energy, and therefore they will not eject an electron. The kinetic energy of the electron, however, is dependent on the frequency of the light. So if you switch from red light to blue light, the blue photon now has higher total energy and thus has enough energy to overcome the binding energy and provide additional energy for the kinetic energy of the electron. The final observation or takeaway is that no electrons are emitted unless the frequency of light is above a given threshold. That threshold is what we call the binding energy, or W.